The first thing we want to do on this example is to determine the minimum number of unknowns that would be necessary to analyze this circuit using mesh analysis. To do that, my first step will usually be to kill the sources. That means I open up current sources, I replace those with open circuits, and I short circuit voltage sources. So let's redraw the circuit with those assumptions. This 10 ohm resistance doesn't change. The 10 volt voltage source gets replaced with a short circuit. The 5 ohm resistance is still there. That doesn't change. The 4 ohm resistance is fine. This 6 amp current source becomes an open circuit, and this resistance is unchanged. Now I identify any enclosed non-overlapping areas in the resulting circuit. This area over here is enclosed, and this area here is an enclosed area. The current source here is now an open circuit, so that connects these two sides of the current source. So the number of unknowns is now the same as the number of those enclosed areas. So the number of unknowns in this circuit is 2 if I'm going to do mesh analysis. Now let's assign some variables to these unknowns. So previously I identified enclosed non-overlapping areas. They consisted of this area and this area. My mesh currents, which are my unknowns, will go around the perimeters of these areas. That means there will be a mesh current going around this area and a mesh current around this set of elements. The names aren't important. I'll call that I1 and this I2. Now if I identify my mesh currents this way, none of them will go through current sources. I need to add constrained loops to account for the current sources. So my constrained loops need to match the magnitude and direction of the current source currents, but those are the only rules associated with them. So in this particular case, all I need is to account for this 6 amp current going in this direction through this element. I can create a constrained loop that's 6 amps here. Over on this side of the world, it's going in the right direction and it has the correct magnitude. That's not the only choice I'm stuck with though. I can do a variety of different things with this. So let's take a look at a few different additional choices of constrained loops. It's perfectly legitimate to have a constrained loop on this side that goes this direction and has a magnitude of 6 amps. It still matches this current direction and the amplitude. A constrained loop that goes all the way around here is also appropriate. It's got an amplitude of 6 amps. Over here at the current source, it's going in the right direction. If I wanted to, I could split this up into 2 different constrained loops. Suppose I have a constrained loop that's got a 3 amp current and another constrained loop over on this side that's going in this direction and also has a 3 amp current. Now, in this element here, the sum of the constrained loops is 6 amps. It's got the right amplitude and it's going in the right direction. You have a lot of flexibility on how you define constrained loops.